Right, so elimination reaction. Most of the time, elimination reaction and substitution reaction, they are going to compete with one another. However, there are some factors that can help us to choose which one is occurring. Now, what's happening during the elimination reaction? So in elimination reaction, instead of nucleophile, we are going to have a base. And what's happening is that the base attacks the proton on a beta carbon through acid and base reaction, moves the bonding electron to form a double bond, and the leaving group leaves. So the product for elimination reaction would be an alkene. We already talked about alkene a little bit. I just want to review some of the concepts that we talked about before. So we can have cis and trans alkene if we have two identical groups attached to a double bond and they are on the same side, we call that cis isomer. And if they are attached to across the double bond in the opposite direction, we have trans isomer. Now, due to steric hindrance, cis isomer is less stable than the trans isomer. Also, we can name the alkenes based on Z and E if we have 4 different groups attached to the alkene. So we need to choose the top priority first. If the top priorities are on the same side, we have Z isomer, and if the top priorities are in the opposite side, we have E isomer. So we talked about it right now that the cis isomer is less stable than trans due to steric hindrance. But when comparing the stability of alkenes, another factor must be taken into account in addition to a steric effect. So we must also consider degree of substitution. So if you look at the molecule that has the formula of C6H12 and draw all its isomers, when we only have one group is coming off the double bond, we call that monosubstituted. When we have 2 groups attached to the double bond, it's a disubstituted molecule. With 3, we have trisubstituted, and then we have tetrasubstituted alkene. Now, the more substituted the alkene, the more stable it would be. So why is that? Basically, it's the similar concepts that alkyl groups can stabilize a carbocation by donating electron density. So if you remember, we call that hyperconjugation. Now, if you have a double bond that has an alkyl group attached to it, we know that double bond is made out of pi bond and sigma bond and interaction of p orbitals to form the pi bond. Now what's happening here is the sigma bond in the alkyl group will donate electrons to the pi bond, and that causes stability to the basically alkene, more substituted alkene. So the more alkyl groups attached to the double bond, the more interaction we would have and the more stable the alkene would be. Now let's look at these examples. So this molecule versus this one, which one is more stable? So this molecule has 3 alkyl groups attached to the double bond, so it's trisubstituted. However, the other one is disubstituted. So obviously, the trisubstituted alkene is more stable than the disubstituted one. Now let's look at E2 mechanism. So generally, during elimination reaction, 3 steps must happen. First, abstraction of beta hydrogen, so this is the beta carbon, abstraction of beta hydrogen by base, formation of carbon-carbon double bond, and loss of leaving group. So during E2 mechanism, all of these steps are happening at the same time. Therefore, the E2 mechanism is concerted. It's a one-step process. Now, similar to SN2 mechanism, The rate of the E2 is also dependent on the concentration of alkyl halide, and here instead of nucleophile we have base. So the rate is dependent on two entities. Therefore, the E2 mechanism, similar to SN2, is bimolecular. And here is the name. So the name also shows that E is for elimination and 2 is for bimolecular. The E2 reaction is similar to SN2, and that's the reason they can compete with one another. But there are some features that can help us to identify the products and decide which one is happening. So SN2 reaction prefers methyl over primary and over secondary, and it is almost unreactive with the tertiary substrate. However, E2 reaction proceeds more rapidly with the tertiary substrate. Now, why is that? So if you consider a reagent such as sodium hydroxide, hydroxide can act as a strong nucleophile in SN2 reaction, and it is also a strong base in E2 reaction. So there are some species that can act as nucleophile and as base, depends on the condition of the reaction. We are going to talk about that later. Now, if you consider substitution on the tertiary substrate, so a tertiary substrate is too sterically hindered. Therefore, the nucleophile cannot approach the electrophilic center. Okay, so this reaction is almost not happening because it is so crowded here. Now, if you consider elimination reaction, this is alpha carbon and this is beta carbon. So it is much easier for the base to abstract the beta hydrogen and form the elimination product. Therefore, elimination is happening over a tertiary substrate faster than the substitution reaction. Now, another reason that tertiary substrate is preferred for elimination reaction is that when you have tertiary substrate, the product, the alkene, would get more substituent, and the more substituent means more stability. So the elimination reaction, especially E2 reaction, it prefers the tertiary substrate over secondary, over primary, and it is almost unreactive. That methyl halide is almost unreactive through E2 mechanism. Now let's look at the example. So this is our alkyl halide, and this is our hydroxide anion. So this reaction is happening through E2 mechanism. Now we want to identify what would be the product. So the first step, since it is a E2 process, is to find the beta protons. So this is the alpha carbon, and we have two beta carbons, therefore we have two beta protons. Now, does it matter which one we are removing? Does it matter if the base removes this one or that one? No. So regardless of which beta proton chosen, you would get the same product because this molecule is rotating in space. So what's happening here is that, for example, the beta hydrogen, this beta hydrogen is abstracted by the base, forms a double bond, and leaving group leaves. So everything is happening in one step in E2 mechanism. And the product would be this cycloalkene, or basically cyclohexene to be specific. So if you remove this proton, you would get a double bond here, but it doesn't matter. It is the same product because this molecule is rotating in a space. Now let's look at regioselectivity in E2 mechanism. So sometimes the beta hydrogens are not identical. So if you remember in the last example, both beta hydrogens were exact the same. So it didn't matter which one gets abstracted by the base, we would get the same product for both of them. Now, when they are not identical, abstraction of either of them can form different products. And this is what we call regioselectivity. So regioselectivity is when we can form different products in more than one region in the molecule, and the reaction prefers one of them more. So to understand this concept, let's look at this example. So this is our alkyl halide. It is reacting with sodium ethoxide and forming alkene product. So E2 mechanism is happening here, and since it is E2 mechanism, we need to find our beta proton. So this is alpha position, and we have 3 beta positions in this molecule. Now we want to focus on this beta position first. Okay, this is my beta hydrogen. Now with sodium ethoxide, so ethoxide is our base and sodium is the counter ion. So the base abstract the beta hydrogen, forms a double bond and kicks off the leaving group. So we are going to form this product. So basically this is alpha carbon and this was our beta carbon. So we are forming a double bond between alpha and beta carbon. We have 2 substituents on an alpha carbon and 1 on a beta carbon. Now if you want to focus on this beta proton, so these 2 beta regions are exact similar, so you would get the same product with both of them. So I'm going to focus on this one. This is my beta proton. So again, the base. Okay, the base abstracts the beta proton, forms a double bond and kicks off a leaving group. So we are gonna get this product. Now this product, we only have 2 substituents on this carbon. Now, so doing this reaction, we are gonna get 71% of this product and only 29% of these. So this is gonna be our major product, and this one is our minor product. And the reason for that is because this alkene is more substituted comparing to this one, therefore it is more stable. So E2 mechanism with the small base such as sodium ethoxide or sodium methoxide prefers formation of the more substituted alkene, and we call that product a Zaitsev product. So it is more substituted product. And our minor product, which is the less substituted product, we call that Hoffman product. So it is less substituted. So an E2 mechanism, so let's make a note of that. E2 mechanism with small bases such as sodium methoxide or sodium ethoxide, and the counter ion doesn't matter, it can be potassium methoxide or potassium ethoxide. So generally a small bases always prefers Zaitsev product, which is the more substituted alkene. And this is the definition of regioselectivity. So in this molecule, we have two regions and we can form two different products. However, the reaction prefers one of them more. So one of them would be our major product here. E2 reaction favors the Zaitsev product, the more substituted alkene with small bases, such as sodium methoxide or sodium methoxide. However, if you use a big bulky base, the Hoffman product would be always favored, and it's going to be our major product. So let's look at the same example that we worked on. So if instead of sodium methoxide, I'm using tertiary butoxide, which is a bulky base, sometimes it can be written as T butoxide. So if you use a bulky base, we are going to form the same product. However, this time we are going to get 28% of Zaitsev product and 72% of Hoffman product. Now, why is that? If you make the model of the alkyl halide, you'll see that it is much easier for the tertiary butoxide to approach the beta hydrogen that is coming off the primary carbon rather than the secondary carbon. Therefore, the tertiary butoxide would make the Hoffman product more. However, when you have a small base, it is easy for the small base to get to either of these protons, and therefore it will form the more stable alkene, which is the more substituted alkene. Now we have other bulky bases that you can use to form the Hoffman product. So the first one that we talked about is tertiary butoxide. It can be potassium butoxide, tertiary butoxide, or sodium tertiary butoxide. You can even use diisopropylamine or triethylamine. You would get the same results, so you would get the Hoffman product. Now let's make a note of that. E2 mechanism with bulky bases such as tertiary butoxide, triethylamine, or diisopropylamine. These are different ways of writing these three bulky bases. Always prefers formation of Hoffman product, which is the less substituted alkene. So in the exam, if you have the option to think about regioselectivity, you need to look for the base. Ask yourself, is it small or bulky? And based on the answer, you can decide which product would be the major product. In the previous slide, we talked about regioselectivity. Now here, we want to talk about stereoselectivity. So if we perform an E2 reaction on this substrate, we have two identical beta positions on this substrate. So this is one beta carbon, and here is the other one, and both positions are identical. Therefore, regiochemistry is not an issue here. Deprotonation of either of beta positions will produce the same result. Now, let's focus on one of the beta positions. So we have two protons on this beta carbon. So when we have two hydrogens on a beta carbon, and when it is possible that we have free rotation about a single bond, we are going to form two products, a trans isomer and a cis isomer. And we already talked about it, that the cis isomer is less stable than the trans due to steric hindrance. So this one is less stable due to steric hindrance. Therefore, the trans product would be our major product. So just have this in your mind. When you have two beta protons and free rotation about the single bond is possible and cis and trans make sense in the products, the trans isomer would be our major product. In the previous example, the beta position had two protons. In such cases, when free rotation is possible about the single bond, cis and trans isomers can be produced, with the trans isomer being more favored because it's more stable. Now, what if we only have one beta hydrogen? So in this case, we need to look at the stereospecificity for E2 mechanism. So here we want to see what happens when beta position contains only one proton. Okay, now consider this structure. So we only have one beta proton here, and you may think that because we have free rotation about this bond, we would get both E and Z isomers. So this one is E isomer and the other one is Z. So you may think that we can get both of them. However, when we have one beta proton, only one stereo isomeric product is obtained, and in this specific reaction is the E isomer. Now, why is that? In the transition state of the E2 mechanism, a base would take the proton, forms a double bond, and kicks off a leaving group. So in transition state, a pi bond is forming, and that involves formation of the p orbitals. So they can overlap with each other to form the pi bond. And in order to achieve this overlap, these four atoms, the leaving group, the alpha carbon, the beta carbon, and the beta proton must be coplanar, meaning that they need to be in the same plane. So whenever we are forming a double bond, the beta hydrogen, two carbons, alpha and beta, and the leaving group must be in the same plane. And whatever is attached to them, to these carbons, can be shown in wedges and dashes. Now here is the model of molecule that we are working on right now. So this is bromine, alpha carbon, beta carbon, and beta proton. They are all in the same plane. So if you imagine there is a plane passing through these four atoms, they are coplanar. And they are shown here in the wedge and dash structure. So bromine, alpha carbon, beta carbon, and beta proton. Now the hydrogen is coming out of the plane of the page on alpha carbon, and the tertiary butyl is going into the plane of the page. So this is the tertiary butyl, and this is the hydrogen. And we also have phenyl coming out of the plane of the page, and methyl is going into the plane of the page on beta carbon. So they are all shown here. This is the methyl and that big group, the phenyl, is coming out of the plane of pH. Now there are two conformations where the beta hydrogen and the leaving group are coplanar. So one of them is this one, where the angle between them, the dihedral angle, is 180, and the other one can be this conformation where the dihedral angle between them is 0 degree. So now let's look at the Newman projection of both to see them better. So if I look at this conformation and I rotate the molecule to see the Newman projection, so in this situation, bromine, alpha carbon, beta carbon, and the hydrogen, they are all on the same plane. Imagine if there is a plane passing through all of these four atoms. And in this situation, the angle between them is 180. So the angle between bromine and the beta proton is 180. So we call them anti-coplanar to one another. Now the other conformation that we can have them coplanar to one another is this one, where the dihedral angle between them is 0. So again, if you imagine there is a plane passing through the molecule, it can hold all of these four atoms, but the angle between them is 0. So we call them syn coplanar. Now here is the rule. To have the E2 elimination happen, the angle between the leaving group and the beta proton should always be 180. So the conformation that can do the reaction is the anti-coplanar conformation. So this is the only conformation that can react. However, the syn coplanar conformation, which is this one, it cannot react and form the product. Therefore, we are going to have only one product when we have only one beta proton through elimination reaction. So with one beta proton, the angle between the leaving group and the beta proton must be 180, and they need to be anti to one another, and they also need to be coplanar to one another. So this is the rule for E2 elimination. Once again, the only conformation that can react during the E2 reaction is the anti-coplanar one. Sometimes you may see the word anti-preplanar, so it's the same thing. So this is the only conformation that can react. And I drew the conformation right here. This is the anti-coplanar conformation, and here is its Newman projection. Now let's draw the product for this reaction. So if we have a base such as sodium ethoxide or ethoxide itself, so the base will attack the beta proton, pushes the lone pair to form a pi bond between the alpha carbon and beta carbon. So since we cannot show that here in the Newman projection, I'm going to push the arrow to the front carbon, and then the leaving group take the electrons and leaves. So we are going to form a double bond. We know that. So let's draw a double bond. Now this carbon would be our front carbon, or basically the beta carbon in this example, and this one is our back carbon, and specifically in this example is the alpha carbon. So the order does not matter which one is alpha, which one is beta. Specifically in this example, the front carbon is beta. In some example, you may see that the front carbon is the alpha carbon. Now the very important thing here is that to the front carbon we have phenyl and methyl attached. So let's attach them to the front carbon. Now since this conformation is only reacting, we are going to end up with one product, and these groups are going to be in a specific location. So to the front carbon we have phenyl and methyl attached. Now to the back carbon I have hydrogen and tertiary butyl attached, and the hydrogen is in a place that is close to the phenyl, so it should be in the same side with phenyl. So this is hydrogen, same side with phenyl, and methyl and tertiary butyl, they are also in the same side. So this is tertiary butyl, and this is the only product that can be produced. Now let's identify E and Z in this product. So this is phenyl is 1, is our top priority, methyl is 2. Now here hydrogen is 2, and tertiary butyl is our top priority. So the top priorities, they are in opposite direction, therefore this is the E isomer, and this is what we expected, that we are only forming one stereoisomer, not both of them. So we are only forming the E isomer in this specific example. Sometimes you may form the Z isomer, so it depends on the Newman projection. The main thing is that the leaving group, the alpha carbon, the beta carbon, and the beta proton, they must be anti-coplanar to one another. This is also going to be the case for cyclohexane. So the beta proton in a chair conformation also has to be anti-coplanar with the leaving group. In order to have leaving group and beta proton anti-coplanar to one another, they both need to be in the axial positions. Now if you look at this conformation and draw its Newman projection, so right here the chlorine is in the axial position and hydrogen is also in the axial position. The angle between them is 180, so they are anti-coplanar to one another. However, if this chair conformation does the chair flip, where the chlorine would be in the equatorial position, and if you look at the Newman projection, we cannot have the anti-coplanar anymore. Therefore, this chair conformation cannot do E2 elimination. And elimination reaction, the E2 reaction, can only occur if we have both the leaving group and the beta proton anti-coplanar to one another. Now, instead of drawing the Newman projection, we have a trick that can be used. So E2 in cyclohexane, to have the E2 happen, leaving group and the beta proton, one of them must be up axial and the other one must be down axial. And to have such a thing happen, they must have opposite stereochemistry or wedge and dash bonds. So now let's look at a few examples to understand this better. Which of the two molecules will not be able to do E2 reaction? So in the first molecule, we need to find the beta protons. This is alpha carbon and we have 2 beta positions. Now to see whether the E2 reaction can happen, we need to look at the stereochemistry of the leaving group. So the leaving group is in wedge. Therefore, if we can have a beta proton that is in the opposite stereochemistry, meaning that it is in dash, the elimination can happen. So because the leaving group is in wedge, the beta proton must be in dash, so elimination, E2 reaction can happen. Now if you look at these 2 beta protons, on both of them I have a dash proton, so elimination can happen in both sides. Now if it happens in the left side, base is coming form a double bond and leaving group leaves. I'm gonna get this product. So remember, the alkene is planar, so there is no point to show wedge and dash here. And if elimination happens in the right side, I'm gonna get this product. Okay, and methyl is still in wedge. Now, which product is more stable and which one is the major product? Obviously the top product, because this one is the more substituted alkene. So the more substituted alkene is the major product. This is our Zaitsev product. And the bottom one is our minor product, which is our less substituted, and it's a Hoffman product. Now if you look at the bottom example, so again let's find the beta protons. So again, in both sides I have 2 beta protons. Now if you compare their stereochemistry with the leaving group, so the leaving group is in wedge and both of these protons are in wedge as well. So the reaction here cannot happen because we cannot have anti-coplanar relationship between the leaving group and the beta proton here. So the reaction does not occur. So as you might notice, to draw the E2 product, we need to consider regioselectivity, stereoselectivity, and stereospecificity at the same time to draw the major product. So in the first example, you notice that I first look at the stereospecificity, that I need to find the beta proton that is anti-coplanar with the leaving group, and then to determine the major product I use the regioselectivity. So while drawing the major product for E2 reaction, you need to consider all of these stereochemistry concepts together to find the major product. Okay, let's talk about a few bases here. For E2 reaction, the strength of the base is very important. And we know that there are some molecules that can act as bases and also act as nucleophiles. However, there are some molecules that can only act as a base and they can only be used in E2 reaction. So one of them is sodium hydride. So sodium is a counter ion. It is positively charged, and hydride is a negatively charged hydrogen. So hydride is very small, therefore it cannot stabilize the negative charge, so it cannot act as a good nucleophile. Therefore it prefers to take a proton from a proton source and converts to the H2 molecule to get rid of that negative charge. So sodium hydride only acts as a base. We have 2 other molecules. They are a little larger, so they cannot act as a good nucleophile to approach the electrophilic carbon because they are very large. So these 2 molecules, they have 2 nitrogens in their structures, and we have lone pair of electrons on each nitrogen. Now here is the question. Which lone pair in dBu and dBn are going to attack the protons as a base. So now think about it. Which lone pair is the most basic one? So the answer for this question is these two lone pairs. They are the most basic one. And the reason for that is because this bottom lone pair on the bottom nitrogen, they are allelic to this double bond, so they can participate in resonance in both of them. Therefore, they are not available to attack the proton and take the proton. So these two lone pairs are the most basic lone pairs in DBN and DBU structure.